Hi, I'm Chris Lowe, and I'm going to be discussing the testing best practices of HPCC systems, both now and in the future. This part of the presentation was brought to you by Atil Lamos, Krishna Tarlapathy, as well as myself. I'm going to start by talking about the OBT and smoke test and the regression test, both overview, issues, and some of the costs included. Now, where does this name come from, smoke test? Well, originally it came from electrical engineering, where when you first connect a device to electricity for the first time, you see whether or not smoke comes out. And if it does, well, usually means the device is faulty. However, if there is no smoke, then there may be a chance that the device is fine. In software engineering field, the smoke test is when a new feature or piece of code is first faced with a large number of tests, like the regression suite. The smoke test itself helps offload an immense amount of testing for developers. If code makes it past the smoke test and the regression test, well, there's a good chance that there aren't any major or glaring issues. And if we check the execution times, we can be sure that there aren't any performance degradations as well. The first version of our smoke test was implemented and executed on a bare metal blade server about 8 years ago. And since then, our initial implementation, we moved it to VMs inside our company's servers, and then as well as a managed OpenStack environment. Our current iteration is actually inside a cloud environment, and there's located in two places. One is inside AWS, and the other is inside GitHub Actions. Now, let's look at some of the differences between both GitHub and AWS. The first main difference you'll notice is that the GitHub action is our official smoke test. The AWS is kind of a shadow or backup system, and it's still up and running and testing all of our pull requests or changes in our pull requests, but it doesn't actually report any of the results as a comment inside the pull request anymore. Another difference is that the runner quota is assigned to our subscription inside GitHub. So if all the runners are busy, then a new pull request or a new push or manually scheduled workflow is going to have to wait until a runner becomes free. Now, for each push, processing has been split into several actions, and some of them are executed in parallel, but each action itself still needs its own runner to be executed. In AWS, the smoke test for each pull request, the tests are handled at the same time on each instance. So essentially, we have about 150 to about 200 IP addresses or for each instance, so we can process the same number of pull requests in parallel. We typically only have about 10 to 15 sessions at any given time. There are differences used in the operating system as well. Most of the GitHub Action ones are run on Ubuntu 22.04. And up until last year in AWS, we used CentOS 7, CentOS 8, and now currently Rocky 8. In GitHub Actions, uh, the actions themselves are initiated by events like pull request. In AWS, the smoke test scheduler is constantly polling for pull requests or if anything else has changed. It creates a new instance and starts the pull request inside of it. The reason for polling is because originally in the smoke test is executed in the company network. The company security wasn't very happy when somebody from outside the network was pushing things into the company. So that's why we went with more of a polling approach to constantly see if thing has changed. Now that it's running in a company subscription of AWS, we're still doing the same polling process because similar restrictions apply. The regression testing in GitHub Actions is actually highly parallelized by the engines and the subset of the regression suite tests. So it could run about 20 or more parallel sections depending on the number of engines and the number of tests that are being submitted at any given time. In AWS, the regression testing is in parallel as well, but it's only based on the engines and use the regression test engines parallel query action to run all the tests. That means each engine can execute several test cases in parallel. Obviously, these are dependent on hardware. Costs, well, Practically all of the GitHub Action ones are free, or at least to the best of our knowledge, right? And based on our legacy subscription. But the big difference is that that has a runner quota. When we're talking about our on-demand smoke tests in AWS, it has costs per instance and storage as well as network. And I'm going to show you some details in a second. OBT, well, that means our overnight build and test system. We use this system to test branches from master to all of our recently active development and support branches. Now, while the smoke test looks at the code before it's merged into its base branch, the OBT is actually validating the current state of the base branches after each pull requests are merged. It's kicked off every night at midnight, and it starts testing in sequence from the branches from master all the way back to one of the earliest supported ones that we have possible. Right now, that includes master 9.8.x and 9.6.x. Officially, no more testing is based on 9.4.x as well as all the previous ones that aren't being built on Rocky 8 because they're older and we officially decided to support Rocky 8. Now, unofficially, however, we do have another OBT machine that's still using CentOS 7 so that we can do pet builds and test all of the branches from master all the way back to 8.12.x. And yes, we still do merge some stuff back into 812x every now and again when it calls for it. Everything is built from scratch every single time so that we're not using any previously built branches. And that's very important. That the only exception to that are our VC package module binaries. The reason being is because one little change in any bit of the code could impact the entire platform. So it's always building everything from scratch. And until recently, OBT was executed inside our company network. So we had dedicated machines for this task. Our dedicated machines allowed us to build and test platform versions in parallel in both debug and release with debug info. Now, these are two different modes. And right now, our current rotation is that 6 days out of the week, we build with release with debug info. And 1 day out of the week, we build with debug only. All right. When we had the dedicated bare metal or virtual machines, on those machines themselves, we installed all the third-party software that we required, as well as the libraries. And all of them were required for the regression test queries, as well as the engines. And we were testing all of those, as well as the embedded languages and all the plugins as well. In the cloud environment, we lost a few of these elements, and we're still working on how to solve this problem properly. So see how we can install all of the necessary third-party libraries and servers. The results of the OBT are always sent by mail, and previously we had a select group of individuals that would get all of the emails, all of the test results nonstop. And they started complaining, saying that they got a few too many emails. So at the current time, we have one OBT admin, and that's Attila, who is receiving all of the test results. Before we switched to VC package-based builds, we had 12 VMs doing our testing behind secured company servers. It was secured behind a VPN, a jump server, single sign-on validation, as well as a very strong proxy server. And this was a bit of a problem for our VC package builds because it needed a lot of things that were blocked by these powerful firewalls and proxies. So we had to move our OBT into AWS. But why AWS and not Azure? Well, to reach our OBT machines in AWS, we actually are able to regularly change our secret keys as well as our tokens so that we can automate a lot of our stopping and starting to initiating our tests. And we don't have that kind of functionality in AKS. Originally, we used one CentOS 7 to do all the testing. And some VC package items were just not backwards compatible. So we had to use two. And right now we're up to four. We're up to like two CentOS 7 boxes, one CentOS 8, and one Rocky 8. However, the CentOS 7 and CentOS 8 ones are going to get retired soon just because the lack of support from the company itself. So the OBT builds everything from scratch, like I mentioned previously, and installs the platform. And then it executes all the WU tool tests and then the whole unit test collection. And that includes both the stress and performance testing, as well as the machine learning bundle tests, because those are like excellent tests for our Thor servers. Finally, it executes all the regression tests on all of the engines. And that includes Roxy, HTHOR, and Thor. And costs. Well, previously, when OBT was run in in-house networks, costs were built in as part of maintenance and running of our data center. And now that it's running AWS, we have more of a detailed cost breakdown, which we're going to cover right now. In this diagram, you can see that OBT and smoke tests are executed in AWS, all right? In the keys on the right-hand side, you'll see several instances that are running in the environment. Some small instances are used as dev environments. So Avon was test, and the two OBT CentOS 8 tests. We have some file servers, and those are listed as smoke test and smoke test scheduler. And their costs are tiny. And all the other servers are that have like OBT in front of them, other than ones that say test. And the on-demand instances, so on-demand smoke test, they do all the heavy lifting. And the total monthly costs range anywhere from like 700 to about $1,000. And this is caused by the increasing number of active branches that we have to support and test in both OBT and pull requests. So as I mentioned previously, CentOS 8 and CentOS 7 are going to get retired soon, and we're expecting the cost to go down accordingly. On to the regression test suite. And it's got two components, right? We have the regression suite itself, and this is where we have all the platform tests that are written ECL. Then you also have the regression test engine. This is used to schedule, execute, and handle, and do all the reporting for either the entire regression suite or just one of the engines that you select. The RTE, or the regression test engine, was originally developed by the platform team as a way to do easy feature function regression testing, but there are some limitations to it. It's got a front end of platform ECL and ECL CC tools, and this is a requirement. We can resolve this by basically just installing the HPCC systems platform package or installing the client tools package. It requires a matching environment of either a cloned HPCC systems platform repo or the entire platform or client tools package. It needs writable user space so that you have space to copy all the whole test suite, as well create log files and temp files. It needs the actual HPCC systems platform for which you're going to test against. So this can either be a local one or a remote one. If it's a local one, it could be either a bare metal installation or a VM installation, or you can have a local set of K8s for a containerized platform version. Then you can do that in either Minikube or Docker Desktop. For remote installations, we have to have it reachable by our test environment, our local environment. And both the ECL watch IP as well as the port addresses have to be known and exposed. And this can either be a remote bare metal cluster or a remote VM, as well as a remote containerized system. And for testing against more customized systems, so if you have multiple Thors, multiple Roxy, so on and so forth, you have to modify the configuration file so that's matching the environment that you're testing against. And this is kind of less than ideal for when you're trying to do easy out-of-the-box testing, right? So that's one of the biggest drawbacks of testing against containerized. By default, in bare metal and VM environments, we have one Roxy, which can handle both work units, so via the work unit queue, as well as publish queries via a network call. And in the cloud environment, however, you have two Roxys. You have Roxy as well as Roxy work unit. The Roxy itself handles the publish queries only, so it doesn't listen at all for the work unit queue. So if anybody tries to execute any of the regression suite tests against it, it's going to fail with the timeout. So on the other hand, we have the Roxy work unit one, which listens to the entire work unit queue, and it can execute all the work units, but it doesn't handle any of the published queries. So if somebody wants to execute the regression, they need to fulfill all of the previous requirements that are there. You have to have a deep knowledge of the target system you're testing against so that you can fill out all the JSON files that handle all the configuration. Moving on to end-to-end testing. What is the need for end-to-end testing? Well, with the focus moving our systems into a cloud-based environment, security has become even more important. And this is extremely important as we make sure all the calls coming to the HPCC system with the HPCC systems, as well as going out of the HPCC systems, are 100% secure. And this is where end-to-end testing comes into play. We test the calls from client to ESP, ESP to Roxy, as well as Roxy to ESP. And there's two different systems that we need to consider while running these tests. So that's both bare metal as well as pure Azure systems. First, let's take a look at the client to ESP. What do we need to consider while testing client to ESP calls? Should we provide server certificates to the clients? Should we use client certificates for authentication for internal calls? How do we configure persistent connections? Should we configure globally or per service? Should they, how many max requests should be allowed on a socket before it's closed? How long can a connection be idle before it's closed? Moving on to ESP to Roxy, and these are going to be very similar. Should we provide the certificates to the clients? Should we use client certificates for automation? Should we configure persistent connections? Should they be configured globally or per service? How many max requests should be allowed on a socket before it's closed? And how long can a connection stay idle before it's closed? Moving on to the Roxy to ESP, should we have to make sure all of these are using HTTPS all the time? Yes. SOAP calls performs. We need to make sure there's server verification as well. Should we allow global configuration in the ECL or in a secret for each call? What about warnings and errors? We need to make sure that TLS is used on all of the internal as well as external calls. We need to make sure that the server is using a TLS 1.3 or later. We need to make sure that client certificates are always available. Ensure that a secret is used for each and every call. We need to also make sure that persistent connections are being used and supported by the server and not closed immediately. And we also need to make sure that persistent requests are explicitly defined. So what do we do for these tests? Well, we created multiple ECL queries in the ESDL format as part of the regression test suite. We created SCAPS methods for calling the ECL queries and for ECL queries to call ESP via a SOAP call. And the figure that is shown there will show that the flow of information, we have ESP method calls the ECL query, and then the ECL queries calls the gateway ESP method via the SOAP call, and then the gateway ESP calls different ECL queries and returns results. And here's an example of our tests, our queries. We designed it with several different options, and most of these are self-explanatory, so I'm going to cover it just in case. We have call direct, which is calling the data directly from Roxy to Roxy call. We have call via ESP. Do we want to call ECL queries via gateway ESP? Is there a document limit? How many documents to return from one of these SOAP calls? Encrypt and connect. This is to test both encrypted and unencrypted connections, so both HTTP and HTTPS, just in case you want to use one or the other. We have ESP-IP, and this is going to be where you define your gateway ESP URL. This is usually provided in the configuration, but for testing purposes, we made sure we added an input option. So persist connection, should we keep the connection alive? Roxy IP, what is the URL for the Roxy? Search words, this is basically our search criteria for the query itself. And finally, we have max results. It's maximum number of results you want to return. Now looking at the end-to-end testing we're performing, this is just the starting point, right? We want to make sure that the system and data flow is secure. There's a few other aspects that will be added in the future, such as securely pass the information to the Roxy pipe process, ESP logging, database, and other services in ESP, as well as the metrics and cache size. Moving on to future plans. We are looking to implement tiered-based testing so that we can properly focus our efforts and maximize our testing versus the severity of the changes that are included. So we typically release with both point, minor, and major type releases, and they all contain varying degrees of impact of changes that are merged. by having a more comprehensive test suite for major releases. And then we have a faster turnaround validation test for like the smaller point releases. We can get the product to our users at a much more timely manner. We're going to continue integrating into GitHub Actions so that we can have more testing and process improvement as part of the whole development process as a whole, right? This is going to ensure that we put forth both due diligence to all our code that gets submitted in. We want to have more users and we want to have them have an easier time reading through our commit messages. Traditionally, our commit messages, actually most commit messages out there, are very developer centric. So these tend to be a little bit hard to understand by most users. Hopefully, we're looking into a more standardized process where the main comment itself is going to be hopefully legible. And then in the details of the commit message is where you're going to see all the developer-centric stuff, so that you can see right at a glance, does this affect the thing that I'm working on? And if they want more details on what actually changed, they can dive deeper into the commit message details. We're also going to work to implement what our intern already started with automated ECL Watch test suite. The groundwork is already laid and we can implement it into GitHub Actions right away. And our goal is to just start adding test cases right away so that we can just have a more stable interface that our users want to use. Speaking of which, we've already started working closely with some development groups and some users, and we created a focus group, right? We wanted to take into account more production and real world use cases. It's not until we actually take our code out into the wild do we actually know how it's used in anger. So we need to make sure that all of our users' concerns are addressed. And with this focus group, we're looking to get feedback from real users out there. So hopefully that we can just refine the ECL Watch interface into something that our users really want to use. It's a critical part of their workflow. So we want to make sure it handles their needs. And this is just a small snippet of what we're currently doing, as well as some of our plans moving forward so that we can make the HPCC systems platform better. Thank you for everybody's time. I'm going to hand things over to my colleague, Michael Gardner now.
Good day. I'm Michael Gardner. I'm a senior software engineer too with the HPCC Systems platform team. And today I'm going to be going over navigating the platform build system with everybody. So a lot has changed in the past few years. First, we're going to go into an overview, the old system versus the new system, and why we ended up deciding to do our change from Jenkins over to GitHub Actions. So first and foremost, the goal of doing these changes was the development of a new and open and most importantly, a reviewable system for building the entire platform and all the associated artifacts. We want to leverage a bunch of new technologies that have come out recently that weren't available years ago when we set up the original system. We want to have shareable build images. We want these to be able to be shared with internal and external developers if they so choose. We want to have a system that was capable for developers to completely mimic our gold build system in case they were making changes themselves and wanted to test the artifacts. So they could use the exact same system that we use for our gold releases. We also want better failure recovery. In a lot of cases in the past, if Jenkins went down, we were all scrambling. So we wanted a system that was a little bit more robust and would be easier to maintain. And finally, we want a fully automated system. In the past, what we've had is there's 2 or 3 people on the team who manually have to go in and set up new builds whenever we do a tag. And it was a lot of repetitive work, a lot of us using templates to make things go quicker. But that also meant that it wasn't a very open process. And if there was two or three of us on the team all away on PTO at the same time, that was always going to be an issue. So we couldn't do it. So let's continue on to look at the old approach. And this approach worked well for years. It was the original system. It was all hosted on premises. We used physical servers for each target distribution. Eventually, then as technologies advanced, we shifted over to using AMIs to describe our target distributions and internally managed OpenStack instance to host all those distributions. Now, the big problem with Jenkins was it wasn't a very transparent process. There was a lot of templates. There was a lot of scripts that were sort of hidden from other developers, not on purpose. It was just a years-long process that we needed to unwind when we built this new system. And it was also cumbersome to back up. There was uh, a lot of headache associated with it. So we moved on to a more cloud-centric approach. The new cloud build infrastructure leverages GitHub Actions as our main build infrastructure for it. It uses the same system that builds official images, can also be used to build any developer's images if they choose to do so. Um, it uses several different technologies that weren't available before. For instance, vcpkg for our C and C++ build dependencies for all those external libraries that we use. It utilizes GitHub as our source code management. It has GitHub Actions as our main build infrastructure, and we also leverage Docker quite a bit, not only to create our own build images that we then share around, but also to push up to Docker Hub, so that way other external developers, if they so choose, can grab those same images and build exactly like us. So let's quickly go over vcpkg and what it is, why we ended up using it, the pros and cons of it. So let's go over what it is first. It's a tool by Microsoft for managing C and C++ projects libraries. So a lot of times what we end up doing is we'll include third-party libraries in certain plugins that we're building with some internal libraries. Let's say, for instance, we want to get uh, like some special use case, we'll grab and include a third-party library. vcpkg has access to all of those, has versioning for all of those that we can quickly link to. And it's also cross-platform. So it means that it works for all of our Linux distributions that we target. It also works for Windows that we target. And it's written with CMake primarily. And for anyone who's ever looked at the HPCC platform source code, we heavily utilize CMake for all of our cross-platform builds. And so having a submodule like vcpkg to do the sort of dependency handling for third-party libraries for us that's already written in CMake, that's a huge plus for us because it's already a technology that we're fairly familiar with. Now, some pros as to why to use it. First off, that single module does the job of a bunch of other older documentations and runtime dependency files. Now, when we go and we build vcpkg and we build our included third-party libraries, those oftentimes will get packaged within our final packages for the platform or for individual plugins. Now, that does increase the package size for those final artifacts, but it also ensures that those runtime dependencies are there and on disk, so there's less hassle for the end user. It also makes it extremely easy to patch security and regression fixes in third-party libraries. Generally, what we would end up doing is if there was a security fix that needed to be made, we would have to wait for the package managers for instance, Ubuntu or CentOS, which is all end of life now, but it's the same process. We would have to wait for them to patch it. Um, if it was extremely critical, we would have to go and basically roll the build of that third-party library ourselves into our own code and include the fix until the package manager is caught up. So it's certainly cumbersome to do it that way. Using vcpkg to handle all of that, because vcpkg ends up pointing straight back to a lot of these source code management tools for the third-party libraries. It makes it extremely easy to quickly patch for security or regression fixes, and also to get new features from the libraries. And in getting those features from the libraries, generally what we do is every single quarter, we try to release a minor release for the platform to include all the new features that we're working on. And whenever we do that, we go through and we update our VC package to ensure that we're getting those newest features for the libraries. The VC package repository that we have is a fork from the Microsoft one. And we include some workflows for generating certain VC package caches that are specific to our platform, and for building the HPC systems platform build base image. This image is then later used in the process to build our final platform build image that is then used by our build process. So let's go into build image generation and let's see what's actually happening here. So in the VC package repository, we build a platform build base image for each individual distribution that we're targeting. These build images are all published. They're all up at Docker Hub. At the bottom of the screen, you'll see a link that you all can follow, and it will show you specifically the one for Ubuntu 2204 here. But if you go into the tags section, you'll see all the specific tags for that distribution for different versions of our platform that we build against. These are all generated as part of our normal release cycle. So the second that a repository maintainer goes and puts a tag on our code and pushes it up to our main repository, these build images start to get generated. And they're all downloadable by anybody. Anyone can go and grab these, use them either locally on their own machines or in their own HPCC platform forked repositories in order to build the platform themselves. So let's hop into platform generation next. So this all is run by the build assets workflow. Workflow files are something in GitHub Actions that are in your source code under .github /workflows. And these individual YAML files describe a process for either doing builds or running tests based on certain GitHub events that can occur. So ours are set up to run automatically after tags are pushed. These create the final build environment. They generate multiple types of packages for several targets. Basically, anything that you could possibly download off of our website, plus a little bit more, is generated by these files. So these are RPM files. These are Debian packages. They're Mac OS packages, Windows packages. And each one of these is basically set up from an OS matrix that we have. And we do this so we can run the same logic on all of these targets in parallel. So we have logic that is the same for multiple OSs. We have logic that is specific to certain OSs. And there's a way of running flags specifically to select for which matrix job you want the logic to run on. Um, but it ends up generating all the platform artifacts, all the plugin artifacts, the client tools, all the different documentation that you'll see up on the website, as well as the ECL IDE. So now you might be asking, where can I find these artifacts? Well, you can go to our GitHub release pages. These are generally not documented for a lot of people, so a lot of people don't know about them yet, just because we weren't really uh, making people aware of them, but you are now. Basically, whenever we do an RC or a gold release, what you'll see about an hour after we do the tagging is you'll start to see these pages get populated. And you can go to the github.com HPC systems namespace, HPCC platform /releases page, and you will see a list of tags up there. And you select the tag that you want, and you will see a drop down of assets. And you can, right from your web browser, download any one of those assets that you want in order to test or run it. We also end up pushing all of these artifacts up to the HPC Systems website. We did a lot of work this summer with one of our interns in order to help automate that process. It's not fully automated as of the time of this recording, but it soon will be by the end of the year. And we also push all these different releases and assets up to company storage. So internally to our JFrog repositories or to internal file servers. And the pushing to JFrog is all automated now. The pushing to the internal file servers as of the time of this recording is one of the very last steps that we just haven't completed yet because it was a lower priority than getting the rest of the system up and running. But a lot of progress has been made, and the system is working very well now. So let's go into detail of a build asset workflow. And we're going to specifically be looking at, I believe, an Ubuntu 2204 with a 9.8.14 tag. So just keep that in mind as I talk about this. So the very first thing that happens within this build assets workflow is you're going to end up hitting the preamble job. And that's just a precursor for all the other jobs. It generates variables that are utilized in the rest of the workflow. Some rather generic information. But then what ends up happening is we hop into the actual build job and we hit a matrix. And that matrix for this specific job will have an OS that's Ubuntu 2204, and it will have the tag that we started the job with, which will be community_9814-1, which will be a 9814 gold release. We clean up space on the GitHub Action runner. We fetch sources based on the tag that I just referenced. Some specific job variables. For this step right here, we generally reach into the source code that we just fetched locally onto the GitHub Action runner. And we will look into the vcpkg submodule there in order to get the hash for its specific point in its Git history. And then we use that information in order to set up a build environment image that we're going to build here. That takes the HPC Systems platform build base image that we generated earlier from vcpkg, and it uses that as a cache for all of our vcpkg libraries, and then layers on top of it. Now that we have that image, we can run it as a container locally on the GitHub Action runner in order to take the runner and turn it into a way of running basically any target distribution that we want. We take our source directories that we fetched earlier. We take build directories that we generate and clean out right before the build. And we go ahead and we mount those into that container. And we run our CMake package logic. This CMake logic is the exact same. If you've read our older bare metal wiki pages on how to build the platform, it's very similar to that. It's very similar to what we used on Jenkins. back in the day. So it's not foreign. It's easily maintainable. And then after this step, what happens? The container finishes. Our build assets are in the build directory that is on the GitHub runner's disk. We take those, we upload them to the appropriate locations. We grab any logs from any failures or any warnings. We take those and we upload that to the appropriate locations, and then the build is complete. So this right here is just a small bit of the logic for instance, the community build. Um, this is going to take the OS matrix. It's going to say, okay, I'm going to run on an Ubuntu 2204 image. We're going to clean out uh, uh, specific directories, create our build folders, and then we're going to go ahead and uh, run the CMake logic. And we do that for every single plugin. We do that for the platform. We do that for client tools. And you can see it all running here. So each distribution target runs in parallel and runs this, which then outputs all the files for us. So that's how the actual build for the platform works for our final artifacts. But we can also use the same infrastructure that we've used for all that for testing workflows. And what will end up happening is we will be able to test every single new bit of code that someone tries to submit to our repository. So whenever we get the on pull request event, because a developer decided to push something up to our repository and request a merge, we have several things happen. We have our test build workflow that's within the build vcpkg YAML file. This builds our Docker test environment that's necessary for it. It runs a version of the regression suite for us and several smoke tests. Then we have other checks for the ECL helper interface. We run test builds on ECL watch to make sure that no changes cause a failure there, and then tests on the Helm charts. Now, for these testing workflows on the left hand side of your screen, this is what it looks like whenever we do a pull request. Basically, this window will pop up at the bottom of your pull request. It'll start cycling through all the different tests that it has to run. Some of them will be skipped dependent on whether or not you touched a certain section of code. For instance, there's no reason to test documentation if you never touched anything within the documentations folder because of the way that we keep things separate. So it will run these tests, and what it'll also do is it'll block your merges if you end up getting any critical failures. And in which case, the only way to unlock that is to either have a successful run after you push new changes, or to have a maintainer override the system. And currently, there's 42 different test cases that we're running here whenever someone submits code to our repository. It's all run automatically. So the actual repository maintainers don't have to do any extra legwork. It's really easy to add test cases to this entire system. And we've had quite a bit of luck this summer during the internship program with interns adding to the system. So this all happens on top of our human reviews. So in review of our new build system and the build infrastructure that we have, it's open and reviewable. So everything for our build system now is in our GitHub repository. So you can review it yourself. You can go ahead and you can look at it. You can go up to Docker Hub with the link that I posted on the previous slide. You can download the shareable build images. And we have the ability now to fully automate our builds. So our repository maintainers don't have to hassle with it, and we can focus more on coding and less on uh, uh, just the builds in general. So these are some resources that you might want to look at if you have any further questions. The documentation you can look at here on your screen for that first link. That's on our HPC Systems GitHub IO page. It's for user build assets. So basically, it's a way for currently our internal developers to run the user build assets scripts. So that way, for instance, if I go to my own repository and I do a tag and I push that tag up to my repository, I will automatically start kicking off builds in my own repository that mimics exactly what I would see for a release candidate or gold release from the main repository. That way I can now go into my own release pages, pull down the artifacts that end up getting created and do a sanity check on them to make sure that they're the correct size, to make sure that, okay, when I go and install them, that there's no issues, there's no runtime issues. And it adds a level of sanity checking that you can do as a developer before you ever actually put up your PR. Some places in the source code you might want to look for resources for the new build system. Of course, the .github workflows directory is going to have a list of YAML files that have all of our test cases. The big drivers that you want to look at is buildassets.yaml. That'll be the driver for our final assets and our packages. And then the driver for a lot of the test cases, you should look at build vcpkg.yaml. Also, if you want to see how the build images are created, you can look at the Docker files /vc package directory that has a lot of that information and allow you to follow it along. And then, of course, if you want to go look over into our VC package fork, that has a very good README, and it also has the workflows under its actions that build the platform build base image. So that's the final slide for me. Thank you very much.